the conclusions from the last hour were that devices consume power, that they don't consume a lot of power when they're not switching, but that they consume power when they are switching, and they all switch at the same time. There's a clock, and they switch at the same time, and that means that we can learn something about the devices as attackers. This was the conclusion from the last hour. Now, this is going to be kind of a fun exploration of what does this help me as an attacker, and I'll get into how can an attacker do it. What is the attacker setup? What do I do with my measurements? I don't think I'll have time this week. So this is the general equation of power consumption of a logic device. This comes from the DPA book. And what you see here is that there are two pieces to the power consumption. There is the static power consumption, and you see it's not a function of anything. And there is a dynamic function, the dynamic power consumption, which changes with time. So the power consumption, the static power consumption, officially it isn't affected by anything that the user is doing. So it depends on the supply voltage, the generation, the kind of silicon you're using, the factory which made the device. Sometimes it changes between device and device, but it's not a function of what the device is doing. As you see, it's not a function of time. It's a function of voltage and so on, of the clock frequency and stuff like that. On the other hand, you have the dynamic power consumption, and this one depends on the circuit activity in the input data. Now, depending on the circuit activity input data, it's really nice for us as an attacker, because this means that I can run this backwards. So if I measure the power consumption over time, and I can solve this equation, and I can find out the secret, then I'm really a really happy hacker. But what you see here is that I need a lot of data about the device to get this, and maybe it's too much. So as I told you, we can make a bunch of assumptions on the circuit. We can simplify this to something which is easier for me to work on as an attacker, and this is what is called the Hamming distance model. Now, Hamming distance and Hamming weight you've all learned, and just to make sure you're refreshed, let's do the autocomplete exercise. I'm going now to the shared notes. And Hamming weight is the amount of bits which are equal to 1 in a number. So Hamming weight of 0 is equal to, fill it in the shared notes. What is Hamming weight of 0? 0. Okay. Hamming weight of 1. What is Hamming weight of 1? What is Hamming weight of 2? Okay, Hamming weight of 3. Oh, okay, thank you. It's 2 because 3 is 1. Okay, this is the Hamming weight. This is the Hamming weight. Now, Hamming distance is the Hamming weight of the XOR. So what is the Hamming weight of 0 and 0? What is the Hamming weight of 0 and 0? No, it's not 1. The Hamming weight of 0 and 0 is 0 because they're exactly the same. What is the Hamming distance? Sorry. What is the Hamming distance of 1 and 1? I mean, okay, what is the Hamming weight of 0 and 1? Okay, right. What is the Hamming distance of 2 and 1? Think again. Okay, it's 2, right? Because this is 1, 0, and this is 0, 1. So actually change 2 bits. So why does this help me as an attacker? So because I am talking about a CMOS device. And I know that the CMOS device in the ideal situation doesn't consume any power when it's not switching. So if I write a vector, I take a vector and say this vector is the value of all of the registers, all of the flip-flops in my device. I can create a very large vector. And then I say once in a clock period, there's a big gong, and all of these registers change their value at the same time, and now they have a different value. And I know, because I'm using CMOS, that only if there was a change between the previous state and this state, there was power consumption. So what I do, and there is a very good development of this in the DPA book. If you find yourself curious about this, I really recommend that you read it. So if I take this vector of the previous state and the vector of the current state, then a good approximation of the Hamming of the power consumption is it's proportional to the number of digital transitions that occurred during this time interval. So if 2 bits change state, it's this, and if 20 bits change, then it's 10 times as much. Of course, the Hamming weight model is not the most accurate model. Maybe if you get better information about the data, you can do better, but it's really simple to calculate. Lido is making, okay. Who wants me to explain this again? Should I explain this again? Okay. Thank you, by the way, for participating so late at night. So I have 8 people who can actually touch the keyboard. It's very impressive. 10. Wow, fantastic. Yeah. So what I'm trying to say, I'm an attacker, and what I'm going to do, not this week but next week, I'm going to say that I measure the power consumption of the device, and I'm going to look at it and discover from this power, it's called the power trace, this measurement, I'm going to discover what the device under test was doing. And to do that, I'm going to write a set of equations, basically, or something else. I'm going to connect the activity of the device to the power consumption. Now, if I was completely using a very, very accurate model, what I would need to do is do a complete simulation of the device, all the cables, all the wiring, all the connections, all the structure, and actually run this through a simulation and see what is the power consumption, how would it look for various kinds of inputs and various kinds of activities. This is very complicated to perform, and it also asks for a lot from the attacker. Maybe the attacker doesn't know how the circuit looks like. So what we're doing is we're doing the simplifying assumption. Simplifying assumption is that A, the device is using CMOS, and 2, the device is using synchronous logic. This is a very, very reasonable assumption. And once we do that, once we assume the device is using CMOS, we say that every clock, a bunch of the bits in the state of the device change, and that the power consumption is more or less proportional to the number of bits that changed in the state. So if more bits change, I would have higher power consumption. If less bits, then less power consumption. And this is an arbitrary simplification, but it's very, very effective. You'll see it is effective because most of the logic devices are CMOS. Very, very good assumption. So what are the units of this thing? What are the units here? What are the units of measure? What is this? Volts? What is this? Watts? No, so actually this doesn't have, it's like bits. It's like arbitrary unit of measure. Once I'm using digital transitions, it's just a number. So you will see that the graphs that we get from the official DPA book don't have any units in the y-axis, which is like a terrible thing to do as a scholar, right? Why don't you have axis values in the y-axis? That is because you're just talking about proportional. It doesn't really matter what they are. Okay, so so I connect